Thank you. Yeah, thank you to the organizers for giving me the opportunity to speak at this wonderful event. As you can see, it's a Blackboard talk, so if you can't see, please just move forward. And there's a lot of pictures, so I've tried to get as much as I could on the board before I started. And so, okay, so, right. This talk is going to be based on a recent preprint from July. This is with two students at Brown, Shaunak D and Marcos Sofronek, in addition to Marcus Sprandlin and Anastasia Volovic. And so in September last year, followed quickly by a plethora of papers in November, and now we're all the way up to the 10th one from Nima last week. Nima and his collaborators have introduced a sort of radical new way of thinking and organizing the scattering amplitudes and the kinematic data. And so one of the collaborators, Hadley Frost, is in the audience today, and he will be giving a little talk later today and probably say much more enlightening things than me here. But this whole sort of line of inquiry or research sort of stems from Nima's quest to find a beautiful formulation of amplitudes that really gets at the heart of what a scattering amplitude is without all this extra baggage that you get from insisting on locality and unitarity when you write down a quantum field theory. So manifest locality and unitarity hard encodes a bunch of redundancy into our mathematical description of scattering amplitudes and makes calculations difficult. So the idea is to look for deeper mathematical structures in which locality and unitarity are emergent phenomena rather than hard-baked into the starting premise. And the proposed way forward is to look at the combinatoric and geometric structure of the kinematic data of scattering amplitudes. And so in this whole line of surfaceology research, this group of people have found very interesting connections to all sorts of areas in mathematics, including dihedral coordinates, positive geometry, hyperbolic geometry, Teich-Mueller spaces, quiver representation theory, tropical geometry, and many more. And so the initial formulation, so the basic idea is to encode kinematic data as curves on some surfaces, which I'll say more about later. And the initial formulation was only worked for bosonic matter, colored bosonic matter. And so it has all these wonderful features that we like to describe the real world, or to have a good mathematical theory that describes the real world. But one obvious thing that's missing is fermionic matter, right? So if this is going to actually describe real world physics, we need fermions. So our goal is really just sort of take a colored fermionic theory, see if we can sort of bottom up, put it into the language of surfaceology. Okay, so I will start by just reviewing what this whole surfaceology stuff is, just sort of intuitively give you a rough picture of what the main objects are. Then I will describe the particular colored Yukawa theory that we're going to consider, give a couple properties of why it's amenable to the surfaceology approach, give you the final surfaceology, or now they're called curve integral formulation for the full amplitude, say a few things about why it's nice, and then I want to go through two examples which I have written on the board here, and then I will conclude. Okay. So as I already mentioned, the idea is to encode the kinematic data of scattering amplitudes on surfaces somehow. So the way this works is that you start with a Feynman diagram, and you can, well, it's pretty easy to see how that's equivalent to this picture here. I just take all of our edges, we just make them thick, okay? And so this is called a fat graph. And this turns out to be dual to a triangulation of a surface, so like a disk or an annulus, something like this, with marked points. Each marked point corresponds to one of the legs. And in this fat graph, we label each one of these roads, or sort of fat edges, by some sort of label, yi. Then, we want to look at the curves, either on this fat graph or on this surface. And by curve, I mean some line that starts from, this external particle number 1, and it moves through the surface to edge 3. It can also spiral infinitely around one of these loops, or in this picture, it would just end on one of the punctures. And so how do we think about these curves? Well, we encode them either in a word or a mountainscape. So the word is really just a string of letters telling us how we have traversed this fat graph. We start at 1 for this example C13. We turn right when we hit, and we go through the road Y1. We turn left, we go through the road Y4, turn right again, go through the road Y8, and then turn left and exit at 3. And so instead of writing this word, it's also useful to have this mountainscape picture in mind. And instead of saying I turn right or I turn left, I just go up or down. Down for right, up for left. And, okay, so now I need to tell you why, or how to encode kinematic data from one of these curves. So the first step is just to really enumerate all the different curves on this surface. Then for each curve, I'm going to assign a momentum to it. So I take a curve, I give it a momentum, and the way you give it a momentum is you take the starting momentum from the starting puncture, and then you add the momentum incoming from the left at each right turn. So in this example of C13, the starting point is this leg 1, so I add P1, and then I've got through this road Y2, in the way I've chosen to route the momentum, I've got incoming L1, so I put it there, and at the next right turn is right here, and I've got incoming momentum from the left P2 minus L1, so the momentum associated to this curve is P1 plus P2. And so you'll only get these momentum that, depending on the loop momentum, if the curve spirals around a puncture. So something like this. Okay, and so one thing I do have to mention is that all of the curves that spiral, we're going to take them to be anti-clockwise, and this is because there's sort of a duplication. You sort of duplicate the data if you take both clockwise and anti-clockwise. I'll say more about that when we get to this one loop example. So after I've enumerated all of these curves, this one right here? Yes, so I have to associate L1, P1, so you get P1 plus, it turns right, and you'll get L, and then it's going to turn left for the remainder of its spiral, so you're never going to add any more momentum, so this is it. There's only one right turn. It spirals infinitely around, yes. Like, no, not really. No, all the momentum are going to look like this. They're going to, there's going to be, you're not, each one of these curves gets like a finite, well-defined momentum. And I mean, there's some tricky bits at 2 loops and higher, in which it gets a little difficult to enumerate all these curves because they can go around one, spiral around one hole, or spiral around one hole for a bit and then go around another hole for a bit, but I'm just really going to stick at tree level and one loop, and we won't see any of these difficulties. Yes, yes.
The only curves that end on that hole go around. You think of this as the sort of picture where you have a geodesic on a hyperbolic surface. If you represented the hole as being at infinity, then you're just thinking of this as some arc from E1 to that point. And then this computation is really just, it's just about the fact that momentum conservation on the surface means that triangles sum to zero.
Okay, thank you for the question. And so after I've enumerated all the curves, generated all the momentum associated to these curves, I need to use this mountainscape. I'm not really, I don't have time to tell you how to do this, but you're going to use this mountainscape and you're going to generate a collection of vectors. So, like, these are called g-vectors. They live in the Euclidean space R to the E, where E is the number of edges. And each of these vectors breaks up this Euclidean space into top-dimensional cones of what we're going to call the Feynman fan. So in these pictures up here, I've actually drawn these g-vectors. And so in both cases, this Euclidean space is R2. So we have some vector t that lives in here. And then we have a collection of maximal cones. And then within each cone corresponds to a triangulation, or in some sense, a Feynman diagram. Okay, and so then the next, the most important thing is that we have these headlight functions, these alpha c of t. So these are piecewise linear functions on the Feynman fan. So that means that they're zero in some cones and something in other cones. And the something that they are, so when they're non-zero, they're actually going to correspond to the Schwinger parameter of this Feynman diagram from this cone. And so these headlight functions are only non-zero if my vector t in this R to the E space is in a cone that contains the curve C. And okay, and there's other objects. So these are sort of non-trivial, but you can also have these, in a cone they're sort of non-trivial, but you can have these theta functions which go just 1 or 0, depending on if t is in a cone with C or not. And so using these functions, you can get sort of a global parameterization for all Feynman diagrams simultaneously. And then it just depends which cone you're in. So if I'm in this cone, because of these piecewise linear functions, I just get that Feynman diagram. Right? I don't have to perform any sum, I just get this global representation. So that's, this G does depend on C. Yeah, so it depends on, so this right here is the curve, corresponds to the curve 1, 4, and it turns out that it's just, 0 minus 1. Yeah, and so in this 5-point example, we have 1, 2, 3, 4, 5 different G vectors. Yes, and we get 5 different cones. Yes, they are. This does work in the non-planar case, yes. Okay, so now I want to move on to our colored Yukawa theory. So the Lagrangian is sort of the most simplest thing you could think of. So we have both fermionic fields, psi bar, and a scalar field phi. These are, that's right, yeah. Yes, I think so. And so essentially a curve is going to represent, a curve is going to end up being like associated to a propagator. So that's why these curves describe, various Feynman diagrams in a cone, right? So a collection of these will correspond to all the propagators you need to make up that Feynman diagram, and those are associated to one cone. No, No, I'm not going to, unfortunately. There's no time. Just, I can only tell you its properties. But the point is that this is all algorithmic. You can enumerate these curves algorithmically. You can get the momentum algorithmically. You can generate all of these functions algorithmically. Right. So we have these matrix fields, psi and phi. That's why there's a trace. They are they have components. You know, phi a is equal. Sorry, phi is equal to. So the claim is that, well, Feynman diagrams, you have this n factorial sort of complexity, right, by summing over all the different things. And this sum is very expensive. And so in this formulation, you're going to have a product. And so if you want to numerically evaluate your integrand, it just collapses to one object. So it's supposed to give a faster way without all this extra complexity of evaluating numerical Feynman integrals. Yes, yes, but there's no point in trying to reproduce it because you introduce this ginormous sum that gives us such a headache in the first place. Right. Okay. So these are fields that we have components. They're matrix fields because these are generators of SU n. Right. That's right. So here we have a curve. Let me go here. That connects 1 and 3. So C1, 3. So if I have a vector t that is in this cone, alpha C13 is non-zero. Yeah. So that means it can participate in this Feynman diagram. If that propagator appears in this Feynman diagram, I need this alpha to be non-zero. Okay. Okay, right. Back to the Lagrangian. So the main features is I need a kinematic term for my scalars and my fermions. The kinematic term for the fermion, well, it gives us this p slash in the numerator of the propagator. And so the main challenge here is how do we encode this numerator structure? It's non-trivial, it's a bunch of matrices. This depends on ordering of the matrices, all this stuff, into this curve integral formalism. And we have two interaction terms, normal trace phi cubed, and this Yukawa guy. And what's very important and crucial to this whole thing is that this vertex is ordered. So if I start with psi bar, psi, then phi, the way that these psi matrices need to be multiplied, you know, the fermionic indices need to be contracted such that the fermion flow always turns right. Okay, and this is going to keep the theory very simple and actually make it amenable to this approach. So as just a concrete example, if I wanted to think about the one loop triangle or three-point diagram, you know, I might try drawing this. But actually, you see that the fermion line turns left here. No, I've messed it up. No, it goes left, right? At the bottom. Okay, sorry. Okay, the point is that it basically, this one's right, yeah, it turns left, good. Right, I mean, okay. So certain diagrams are allowed, certain are not. And, okay, so as you can see in these pictures here, there's a sort of special property here that all fermions need to be, and antifermions have to come in adjacent pairs. Because of this turning right, the fermion flow has to exit as soon as possible. So you can't really. That's right, yeah. Yeah, so it turns out that there's no way to make this diagram using this vertex. This is the only vertex that you have that. well, so if I turn this guy, I have to come in psi, and then psi bar has to come in on the left. This is forced, so I can't go around the right. It's just not possible. Yeah, the right side has to be is a scalar, and it's fixed. It has to be a scalar. Yeah, so it has to go psi bar. Okay, actually, let me skip a few things, and thank you for all the questions, but let me just actually skip to a few points here. So, good. Okay, so one of the main features here is that so when we get to loops, we can have closed fermionic loops, of course, and also loops that are just scalars. So we need to be able to account for that in whatever our tropical numerator is that we want to use. And that when we do these triangulations, we have to assign, in addition to just triangulating, we have to assign some sort of species to each one of these curves. It's either a fermionic curve or a scalar curve. So I've drawn all of the fermionic stuff in red in these triangulations. So at tree level, everything's actually fixed. You draw your fermionic outer guys and your scalar outer guys. And then if I want to triangulate using the curve 1, 3 and 1, 4, it's forced to be fermionic. These are going to be fermionic propagators, as you can see right here. Okay? And at tree level, this is completely fixed. The only ambiguity at loop level is just if I have these closed fermionic guys, I can choose either fermionic or scalar. And so, of course, you get some chain of matrices when you do the Feynman rules here and here. But the amazing thing is that the order in which I multiply these matrices as a function of the curves is completely fixed across all of the cones. So what this means is when I build my numerator, I can just, there's actually a fixed order for these. I can just go PC1, PC2, and this order remains across the entire cone. Okay, so let me expand a little bit more on that here. So the actual formula for these surface integral expressions of these amplitudes for phi cubed is the following. You take an integral over the loop momentum and then integrate over the Feynman cone, e to some action. This action is just sort of the normal Schwinger trick, where I've got some tropical headlight function. That's the tropical version of a Schwinger parameter, and some momentum from the propagator squared. And you can actually perform this loop integration and get a representation that doesn't depend on a loop momentum, and this is the global Schwinger representation. So depending on which cone I'm in, which depends on this t vector, I just get the Schwinger representation for that diagram. Okay? And now, so what do I need to change in this formula to give a colored Yukawa theory? And the answer is I just need to insert the correct numerator, accounting for all these chains of p slashes. So what is this numerator? Well, I've written it right here. So the first term is just, I need to account for every sort of external trace, fermion trace. So a trace going from one external fermion to another external antifermion. And so so I need some chain of p slashes sandwiched in between two external spinners. Now, this chain of p's, I'm going to put a little path ordering symbol right here in red. And then I just put every single p slash of t. This is a new tropical function I'll get to in a second. And I just put for every single possible curve that can appear in between, in a propagator that connects these two fermions in a trace, I just put that in there. And this path ordering thing is sort of what I mentioned earlier about, it gives a definite order on the curves. And it orders the curves in such a way that all the p slashes are contracted in this matrix product in the right way. And importantly, I don't always want to get a p slash. Sometimes I want the p slash to be a 1, right? Because sometimes a fermionic propagator doesn't appear and I don't need a p slash in the numerator. So using these headlight functions and these theta functions that I introduced earlier, you can write down a tropical version of p slash. So this is just the normal p slash when my vector t in the Feynman fan is in a cone containing c and one otherwise. So I just have to write this product of tropical p functions, tropical p slashes, and then as my t vector moves over this Feynman cone, I automatically collapse onto the correct numerator. So that's the first guy up here. That's at tree level. At loop, I have to add 2 terms, multiplying the whole, because these are just with respect to external guys. So now I have the possibility of internal things happening. So this stays the same, and I get a new term. And it's the same sort of thing. I just need to add a chain of p slashes for all of the different curves that can appear in one of these internal traces, ordered by this path ordering, which, let me stress, is algorithmic. It's just based on the mountainscape of the curve from earlier. And of course, I have to have these theta functions in here just to make sure that I don't make any bad left turns. But these have an explicit expression in terms of the thetas and headlight functions introduced earlier. Okay, good. So now, hopefully I have time to write some formulas from these examples. 3 minutes or 5 minutes or something like that. Okay. No, this is part of the whole thing. We wanted to see, can we do this? Can we start from sort of like a very naive bottom-up approach and just say, I want to see if this theory works, right? And okay. And so I think the general understanding is that like it will work if the curves basically encode everything about what's happening in the Feynman diagrams, right? Like here, I sort of said that, like, you know, even after I put species assignments to these curves, it's still just fixed, just by the curves themselves, right? So you need this sort of property that, like, these curves are kind of uniquely fixing what's happening in the actual Feynman diagrams. So I think if you have that property, which it turns out that, you know, these sort of colored theories seem to do, then yeah. So, but you know, if I added maybe the other ordering of this vertex here, things might get a little messy, and I don't know. No, I'm not sure. Yeah, yeah. Yeah, yeah. Well, there's some subtleties about that, but at least in the examples I'll present, yeah. There are no gaps. Yeah. Yeah, asterisk or quotations, but yeah, basically no gaps. Yes. Thank you.
It's a tropical geometry version of a global function on the moduli space of Riemann surfaces that looks like a cross ratio, or behaves like a cross ratio. More on that later.
Yes. So let me just write down this tree example, and so I at least show you something interesting. So in this case, this numerator function, it's, well, I only have 2 fermions, so I've got V1 bar. Oh, there we go, that makes much more sense, good. So I have this path ordering symbol. I have this tropical p slash function, C13. So yeah, maybe let me stress that. So in all of these triangulations, C14, C13, C14, these curves C12 and C13, they're forced to be fermionic in all of these cones, and they're the only fermionic curves can appear in a trace. So I'm basically going to enumerate all my fermionic curves here, C14, T, and then close this off with the spinner U5. Okay, and then, okay, so then there's this path ordering, and it turns out that it basically is just whichever one of these paths turn right first, and it turns out that C4 comes before C13. So I can actually write this as V1 bar, P slash C14, P slash C13, T, and then close it off with this spinner. Okay, so now I just wanted to show you how this formula actually collapses to what you would expect from these Feynman diagrams. So if I restrict to this cone right here, which includes the curves C13 and C14, this tropical P function, well, both of them are going to just go to the P slash because this cone contains both the curves C13 and C14. So if I restrict to this cone, C13, C14, I get V1 bar, P slash C13, sorry, 14, P slash C13, U5. Okay, and you can see that this ordering is actually compatible with what you would expect here. And if I tell you what the momentum are, you get V1, P slash 12, P slash 123, U5, right? So we've got momentum P12 running through here, and P123 running through that propagator. So what about this cone up here? This cone contains the curves C13 and C35. So this formula, if I restrict to that cone, C13, C15, I get the following formula. Let me just not make a mistake. So V bar 1, yes, so P slash 12, identity matrix, and U5. So the tropical function, P13, has turned into the identity matrix here because it's not contained in this cone, and that's exactly what you need for this Feynman diagram because you only have one fermionic propagator and it depends on the momentum P12. So I should only see a P slash 12 in the numerator. Okay, so I think I've used up all my time. I still have 10 minutes? Oh, okay. See, I thought I had to, okay. Okay. Thank you. Okay, good, sorry. I thought I had to rush there. Yes. Yes. Yeah.
Then in principle, you're telling me that I just need to compute one big matrix product.
That's right.
Right?
That's right.
So then I have a matrix.
Yeah.
Which is some M. And is there something nice about the entries of that matrix?
So.
Here we're doing the opposite thing. We're sort of disentangling everything.
Yes, that's right. Yeah, so looking at the matrix, keeping in this functional dependence on T, essentially. That's something we haven't looked at, but that's a very interesting question. So I don't know if I have.
Lots of relations between functions. So maybe they.
Yeah, perhaps. This is a good question. We should look into it. Thank you. Yeah, there's only one fermion line through the graph. Yeah.
Right, but this continues to work when you have 6 pairs of fermions. There's just one matrix for each pair.
For each pair, yeah.
Describes all possible spaces at any number of points.
Yep.
And loops. And loops. Modulo your turning right versus left.
Modulo turning right versus left. Yeah, and so that's actually important in this one loop case. Because in the Feynman fan, I already sort of mentioned that there's this redundancy of having clockwise and anti-clockwise spiralings, and we just choose one. So this part of the fan, at least in our conventions, corresponds to clockwise spiraling, and we're choosing the anti-clockwise just conventionally, so this part of the fan we don't need. And then, moreover, in this part of the fan, you have the only type of triangulation you have here would give you graphs where your fermion turns left. So actually, there's no graphs. We have to turn this cone off, actually, completely. And so we've done that in this formula for our numerator by just hard coding some theta functions here that just vanish whenever we're in that cone. Okay. Oh, this one right here. Okay, so I was just going to do the same sort of demonstration here, show you that you get what you would expect from Feynman diagrams from this approach, even at loop level. So in this case, the numerator is equal to, we have one product for the pair of external particles. Because it's a 2-point function, there's no path ordering really because there's not enough p's that appear. So I can just directly write down what it is. So C2, 0 of t, U2. Then we have this theta, no left, minus theta, no left. And then we have a trace of p slash C10 of t. Okay. So we have two possible cones that we know will contribute, since we've already killed one with these no left theta functions. So the first one is a bubble diagram. So if I restrict, so what are the curves that appear in this triangulation? Well, we have a C, C20 and a C10. So C20, C10, and what we're going to get is that this product collapses to the following thing: V bar, L slash, minus P1 slash, U2. So this just comes from this external trace right here, which connects these two external guys. So there's no internal thing. So that means that this guy's not contributing. And then this basically just gives a 1 coming from the contribution from the phi cubes. And this is exactly what you'd expect from this bubble diagram. It gives you the numerator of that guy. This guy is a bit more interesting. We have two possibilities. So if I restrict to this cone, which has C10 and C11. Okay. Then we have these two possible Feynman diagrams, and this formula becomes the following. Well, there's no internal propagator, fermionic propagator here, so these spinners become sort of the trivial product. U2. And then all the action happens in this part of the formula. Well, we have one contribution from where we have a phi cubed loop. So that gives us just a 1. I've set all the couplings to be the same here, just for simplicity. And then the other guy gives us a trace of L slash. And so that's exactly what you'd expect for this type of fermionic tadpole. Okay, and so I've tried to illustrate that at the loop momentum or like loop integrand level, that this formalism is reproducing the Feynman diagrams correctly as we go through all the different cones. And there's one more incredibly amazing fact, is that this loop integration right here can actually be performed to get a global Schwinger parameter representation for these amplitudes, just like the trace phi cubed. And after you perform this loop integration, you get sort of these Schwinger things where the new, there'll be some modified numerator because it's a Schwinger parameter thing. It doesn't depend on loop momentum anymore. But every object in there depends only on the curves and is just some determinant. So it's this nice combinatorial formula. And so this was actually a complete surprise, and we never expected that that would work, but it does. So we also have this sort of global Schwinger parameter representation for this fermionic theory as well. But okay, I don't have time to go into any of those details. Yeah, that I can get a closed formula for what the Schwinger parameter. Yes, 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 yes. So there's a closed formula for doing this loop integration. And all of the objects that, sorry? Even with the numerators. Yes. And then every object that appears after this loop integration is just determinants. So it's all combinatorial. I don't have time. And it would I'd have to introduce some determinants and write some formulas. But I'm happy to, it's in the paper and I'm happy to chat afterwards about it. Okay, so now I'm at the time limit. Yes, good. Okay. Oh, I was gonna. Oh, sorry. I was just gonna conclude. Yeah. So to conclude, what we've done is we've shown for the first time that actually the surface integral picture can be used to describe fermions, which gets us one step closer to using this technology for the real world physics. And so, admittedly, we had to rely on some special properties of this particular theory and its Lagrangian. But you know, it's still a promising step forward. We performed a bunch of extra checks. We went up to 10 points in the tree level, not full 10 points, but you know, various checks there. And we went up to 2 loops, 4-point various checks there as well. So on our to-do list would be like, you know, so everything was done with massless fermions. So how do you include masses, you know, if we want to look at QED or something like that? Or even if we want to do massless QED, we would need to understand how to work with fermions in the fundamental representation, not the adjoint. So everything here was done in the adjoint. Yeah, and so it would be nice also because a lot of these curve integral formulas, they have some sort of stringy avatar above, in which this formula is literally the tropicalization of this stringy integral. And so it would also be really interesting to see if we could find a formula like that. And that's everything. Mm-hmm. Mm-hmm.
Is there a way to look at this loop integration principle work in some equivalent slides or something?
The y's are more like coordinates on the on this cone than actual tied to being loop momentum. I'm not sure if I have a good answer for that. Yeah. In the string theory case, yeah. Yeah, this is the tropical version, and those things are being set to zero by this limit, by taking this a certain limit. So it'd be great to try to find this stringy integral, which is somehow, it knows about all of this. You need like RNS, something. You need fermions on this world sheet somehow, right? Like, yeah. So I don't know how that would fit into this tropicalization picture, but perhaps it can be done. Hmm. Yeah. Well, of course, the end goal would be to do the standard model. That's a bit ambitious, I think, at the moment. But I do think that one of the most pressing problems in this whole surfaceology business is that, like, how do you deal with uncolored matter? We have lots of uncolored matter. So if this is actually going to be the silver bullet that we'd like it to be, this the gravity. Yeah. And yeah, the Higgs. Yeah, we have scalar particles. So how does this work for just like a Higgs? These are very important questions. Is it? Well, yeah, it has some. Yeah. Sorry? Well, I mean, I don't know. Maybe Hadley can say more about this, but there's a section called the shadow of gravity in one of these papers where they talk about how the curves that correspond to graphs where where's the first one that this comes about in? I guess maybe this alien graph. It's just a 2.2 loop surface. And if I draw some curves on here, there's some curves that sort of like, that has to do with this, some open string?
Yeah. If you thought of this as being a sphere that you've removed 3 open string trace factors from,
Sure.
then the curves that you're drawing now that go around the trace factors are like internal gravity propagating.
Ah, okay. Yes, okay. So there should be there are these curves that correspond to going around these guys, which, yeah, somehow is some shadow of gravity. And this has to do with this complicated, I actually meant to just say in words what this is, but I forgot. But there's this object here where I'm modding out by the mapping class group in this integral over the Feynman fan. And this is very much connected to the whole story with the existence of these type of curves, which should somehow know about gravity.